All right, we're just going to do a quick tutorial on this whole idea of work and how it causes a change in energy. So if we remember this concept of work, and most students in middle school learn that what is energy is the ability to do work. Well, what do we mean by work? We really need to understand this concept of work. So there are three things that we've learned already that constitutes whether or not we're doing work. One, that there has to be a force that gets applied, a push or a pull, and that force has to cause something. So it's either going to cause something to change its location or speed up or slow down, those kinds of things. And then the other big condition that we can tell that work is being done is that it has to move. It has to change its location. So when we talked about a guy pushing against the wall or a weightlifter holding the barbell steady above his head, at that point they're not doing any work because the barbell isn't moving, the wall isn't moving, those things nothing's happening. You have to have all three of these things to go on in order for work to be done by that force. And what happens when we have all of these things together and we do work? It's going to cause change. And change is what it's all been about. We've been talking about change in speed, change in location, change in anything. But now we want to look at it from a lens of a change in energy. And you guys have studied energy before, and we know it. It's potential energy, kinetic energy, and we're going to talk all about that. So when we look at our definition of work, the formula for work is that force exerted over a distance. So I take force times distance, and that is going to give me work. And the units that I measure work in is a joule. Just like a diamond or a ruby, it's called a joule, so we can use capital letter J for that. And because work causes this change in energy, energy also has the same unit because work is equal to this change in energy. So these are the big ideas that we want to understand about work. So now we want to move on to the next level of how do we see when work is being done. All right, so there are basically two cases that we're going to deal with. One is kind of motion along this horizontal direction, and the other one is the motion of lifting things up. So the horizontal direction, I think people tend to not have too much trouble with. It kind of makes sense. So let's just go over that one quickly. So if I take some kind of box, right, and it's on the ground, if I want to move it to some other location, so I'm going to start here at position 0, and then I'm going to move it to some location, I don't know, maybe like a meter away. This is going to change it some distance. Well, in order to make it move over here, I'm going to have to apply a force. This is my applied force. This is the force that is doing the work. This is the one that is causing the motion to go from here to here. And of course, we remember we have other forces here, like this is our normal force, and then you're going to have your weight vector down. But these two forces aren't doing any work because they're perpendicular. They're not causing this change in motion. So what we see here is that the work being done is, again, our same formula. This is the force that's causing the change in location and the distance d. But there's another connection that we need to make here, and we need to go back to the previous units. If we look at this force diagram, we see that these are unbalanced forces. What do unbalanced forces cause? They cause acceleration. What does acceleration, how do we recognize it? We're going to see a change in speed. Now we're going to make a connection here because I know you guys have studied kinetic energy before. So remember, kinetic energy is all about that energy of motion. And we're going to talk more about kinetic energy a little bit later. But if we look at this diagram and we can see that, well, maybe it starts at rest and moves over to this distance, it's going to cause it to speed up. I'm going to add energy. And that's as far as we have kind of gotten early in the game. But we know that it's not just any old energy, it's going to be adding kinetic energy. And we're going to return to that a little bit later. So this work done, the force applied over that distance, is going to cause a change in energy. How much work is being done? Well, it's going to be exactly equal to how much the kinetic energy changes by. Exactly equal. We want to make that connection between the work and the change in energy. And we just need to be more specific about what kind of energy we're talking about. All right, so that one usually is fairly straightforward. And what's the second thing that can come down? Well, when we talk about something that's slowing down, well, it could be that's changing its speed. We can talk about something that's slowing down. And what causes something to slow down? So again, let's just say we still have motion this way. And it starts at this position, and maybe like at 1 meter later, now it's at rest, not moving at all. Well, friction is going to cause, remember, cause it to slow down over that distance d. So now we're losing energy due to friction. And this is work being done by friction. So how much energy do we lose as it goes from some speed to no speed? Remember, it's losing its kinetic energy. Well, that work that's being done is going to be equal to that force of friction, that's our force, times that distance d. So that's how much energy is being lost. And where is it going? It's going into heat. Oops, lost my marker. It's going into heat. So just for a second, take your hands, rub them together, and you're going to feel that they're getting warm. And I know you're not rubbing your hands together because you're watching a video, but you know what the experience is. So what's happening here? We're seeing a transformation of energy. So how am I able to rub my hands together? Well, I eat food every day. That's chemical potential energy. And then my muscles cause my hands to move. That's kinetic energy. And the more that I rub my hands together, I'm going to start to feel that heat. So I'm seeing that transformation of energy from one to the next to the next. And that is our big idea that we're going to be covering this unit. So friction can also cause that loss of energy because of it's sliding, and it transforms some of that energy into heat, which I know you guys have studied before too. So work equals the force times the distance. That's not changing. All right, now we want to get to the challenging one. The challenging one is the potential energy, because we have to make connections, and that's like the big deal. So if we have a box and I want to lift it up, again, I'm lifting it up a vertical distance, but we don't usually just call it any d. That's supposed to be a d. We can say that that is some height, right? Because usually we don't say, oh, I lifted it this distance. Usually we say, I lifted it to some height. And we get to this new location. Now we need to understand that now this work that's being done to lift it up is changing the gravitational potential energy. We still see the same work formula is equal to the force times the distance. But now we need to kind of answer, well, what are we talking about here? Well, we already kind of mentioned that we can call this distance h, the height, right here. It's just kind of a different name for it. But now we have to make a connection about what's going on with this force. Well, let's just draw another quick diagram over here. If I want to lift something up, how much force do I need to apply? Here's the connection. Well, it's got a weight that is pulling it downward. If I want to lift it up, this person has got to apply a force that is exactly equal to the weight. So the applied force to lift it at a constant speed is got to be equal to the weight. And this is the connection that we need to make to recognize that this force is the applied force, and that applied force is equal to the weight. And if we go back, and there's no excuse here, we need to kind of know this formula, how to go back and forth, that the weight, and I'm going to write it out because weight and work all start with W, so I don't want anybody to get confused, is equal to the mass of the object times what we call that gravitational field strength, M times G. So that applied force, which is equal to the weight, and we need to remember that the weight is equal to the mass of the object times the gravitational field strength. That is what gets applied in there. So now when we look at our work formula, and I'm kind of running a little bit out of room here, go back to my blue marker, our work, which is force times distance, is going to be equal to the applied force, which is going to be equal to the weight of the object times the distance I lift it, and I'm going to call that h. And we recognize this formula as the potential, the gravitational potential energy of an object. So again, the work done, force times distance, that hasn't changed. We just kind of plug in what we know about that. And that is our big idea. All right, hope that helps.